I'm just simply doing a welcome on behalf of the IAS, and I welcome everybody virtually and live in person today to this fantastic seminar by Ben Goddard. And one of the things that has been wonderful about this, and I'll be turning over to my colleague David Sibley from Mathematical Sciences shortly. Ben has been working here with David and also with Andrew Archer and other colleagues during the course of a couple of weeks now. And we've been really, really enjoying this visit and really hoping that our space has felt welcoming and has really enabled you to get on with some fantastic work. And as I was saying earlier, I am not a mathematical scientist. And one of the things that I have enjoyed most is watching our whiteboard fill with what to me are like fantastic, amazing hieroglyphics. And they have been thrilling and of course changing as the course of the work has gone on. And what I'm really looking forward to today in listening to you, Ben, is to the idea that you might actually translate some of those hieroglyphics into something that I will be able to understand as well. And I will be thrilled to know what you've been working on while you've been here. And if I can turn over for a moment now to David Sibley, who's going to do a slightly more formal introduction for you, and then we'll proceed. Thank you.
Thank you very much. I don't know how formal it'll be, but very much welcome to everyone in the room and to the people online. Yeah, it's been brilliant to have Ben and also brilliant to have us to be able to use the space of the IAS. It's been really, really nice few weeks, and I think we've had quite a few PhD students drop in and other collaborators and things, and it's been really great. So anyone who's thinking about whether they should invite someone to come here, I'd say definitely. But yeah, so thank you very much, Ben, for spending your first few weeks of your sabbatical with us in Loughborough. Ben is a reader at the University of Edinburgh and the Maxwell Institute for Mathematical Sciences. We've known each other for
since 2013
years, because we shared a couple of offices at Imperial College as postdocs, but Ben started his well, I guess not started, but was an undergraduate and did postdoctoral master's and PhD at the University of Warwick, and then spent some time in Munich with Evaporation. Before moving to Imperial College as a postdoc, and then from there to Edinburgh. And he's a specialist in a wide range of applied maths and physics, but in particular has sort of inspired us with a lot of his brilliant numerical work. And I think there's a lot to come out in the next few months, hopefully, or a lot of work for us to be doing that he's helped us with. So thanks again, and yes, we'll enjoy your talk on modelling the coffee room.
Cool. Thank you much. Thank you to the IS for having me. It's been excellent. It's really like having a retreat and getting to do some actual research, which a massive novelty, to be quite honest. So I'm going to tell you about the coffee ring effect and in particular modelling it. I will be starting with something much more basic than that because I'm a mathematician, and I'm going to start with something simpler, but I'll tell you what that is in a minute. This is joint work with Jan and Carmen, who, unlike as David pointed out, this should be a 2, so there's a type on the first slide. Genius. They're in physics at Edinburgh. And in case anybody doesn't know, the Maxwell Institute is the maths department at Edinburgh and Have It What, which is also in Edinburgh, and we're combined for all of our research activities. So that's what Maxwell Institute on everything you know about Edinburgh. So I thought I'd tell you a little bit about me. So what I generally do, I would describe as complex multi-scale modelling. I'm going to be doing this thing that I tell all my students not to do, which is looking away from the audience because my slides are over there. So please forgive me. If I'm looking over here, you have a question, just yell. So I work on a whole range of different topics. So mathematically, I classify these as modelling, analysis, and computation. So I generally work, I was trained as an analyst, but I basically only work on analysis when I think the problem is interesting for modelling or computational reasons, rather than proving theorems because I think I can. So that's where my research has ended up in. I'm not sure my PhD supervisor would approve, but that's how it happened. And then almost everything I do is interdisciplinary. So David mentioned that I was in Imperial. We were actually chemical engineering together. My PhD was in mathematical quantum chemistry, and I worked in mathematical biology. I work with people in informatics/computer science, work with quite a few physicists, and I also work on some stuff in social science. So I have a fairly broad interest. Basically, if you can explain to me why the problem is interesting to you, then I'll probably also be interested in it and add it to the list of things that I'm never going to get finished. But we'll see how that goes. So Show you about Yob and Carmen. So Yob is a reader in experimental physics at Edinburgh. We met because they gave a seminar to their complex fluids group, and then 3 years later, he got his PhD student to email me and said, "I saw you, my supervisor saw you doing this modelling on this thing. Would it work on what we're doing?" And my initial answer was no, but there might be a different way of doing it. And then Carmen has recently defended her PhD where this was part of it. So for anybody who doesn't know, the coffee ring problem is that you take a droplet of coffee and you put it on a surface and you leave it to evaporate, and quite often you get a ring-like pattern around the outside. So there's more of the coffee colloid nanoparticles, whatever you want to call them, deposited at the edge of the droplet than there are in the middle. So people want to understand this. One, because it's quite an interesting fundamental question, but the other reason is that often in industrial applications, you don't want this to happen. So you would like a uniform coating of something that you apply. So if you want to stop this happening, it's good to understand why it does, and then maybe you can counteract the effects that cause it. So that's really Yob and Carmen's motivation. They're working with a company who works on spraying pesticides on crops, and they want to make sure it's uniformly distributed rather than forming rings on the leaves where it tends to burn the cells and things like that. So that was their motivation. My motivation was it was an interesting problem. So this sketch on the right is sort of a heuristic of reasons people think you may or may not get a coffee ring. So this is a flight through the droplet in 2D. And if you get a coffee ring, the conjecture is that you get these flows that drive the particles down and out, so onto the surface next to the edge of the droplet as the droplet is evaporating. If you don't get it, the conjecture is that you get some form of circulatory patterns, and then they deposit reasonably uniformly across the surface. So I'm going to try and understand if this is the only possible mechanism, or whether you can describe this in a different way. So can you get coffee rings without necessarily putting in all this background flow and solving some hydrodynamic equations? That's mostly motivated by my background. Let me show you an experimental result. So this is not going to have a coffee ring. This is just the evaporation of the droplet. So the first thing we wanted to check was that our method will accurately reproduce the evaporation, because if it doesn't, the chance of getting the coffee ring correct is essentially 0. So we're going to start with a pure droplet of water, which is this blob on a surface, which is the grey stuff. This black bit at the top is the droplet that they use to put the droplet on the surface. It's actually used for computing the scale that you're at, because they know exactly the width of this. So you can convert your pixels into whatever units of length you would like to use. And then this green is a fitted part of the circle to the edge of the droplet, which is what the experimentalists like to use. Turns out that their fancy bit of kit comes with fitting software, which is garbage. So I wrote like 10 lines in that lab, and it works better than this £10,000 bit of kit. So maybe, should go and do that instead of doing maths. So what I'm going to show you is what happens as this evaporates. The time scale of the whole movie is on the scale of about 20 minutes. But this is obviously sped up. So what you see is, in this case, the base of the droplet is almost fixed, right? So there's sort of 2 main ways you can think of something evaporating. So you start with the droplet. It can either evaporate by fixing the base and then shrinking down, or you can fix the shape of the droplet and just get smaller. Those are sort of 2 ways. If you ask somebody how do droplets evaporate, those might be 2 sensible options. We'll talk more about that later. This is in some way caused by the surface roughness, so your droplet sticks at a particular base width and then evaporates. At least that's a theory. Yeah.
What's the material?
It's PDMA coated in something. I can't remember what they doped it with. I'll show you some examples later where they've covered it in different things, so you get different equilibrium contact angles. So that was that. Let me move to the next slide. So I'm going to show you the mathematical model we use. It's a 3D model, but in the end, we're going to be doing numerics in 2D because it's much cheaper and it gives you reasonable results. This is based on some work by Andy Archer and collaborators. So I should admit, I took what I thought was the correct model, implemented it numerically in our fancy code, and it doesn't work. And I was like, oh, maybe I'll try Andy's method instead. And Andy's method does work. So this is why I'm using this one. So if you look at the picture to start with, you think about taking your experiment and discretizing space into squares, let's say. So these are these squares here. I have a wall at the bottom that I've marked in grey. And then each space should be roughly the size of a particle. So then it can either be full of a colloid particle, so a coffee particle, or water, which is the blue thing, or be empty. So you can be one of three states: empty, copy, or water. You can have at most one in each thing. So you can't have water and copy in the same space. They don't fit. Okay, so you have this sort of lattice where you discretize it with, let's say, your particle diameter. It doesn't have to be. When we do the numerics, it's on a much bigger scale, but that's sort of what you would do if you had a very powerful machine and were willing to run it. I'm going to label these lattice sites by a vector, ijk. So these are the three x, y, z coordinates. Later they'll just be ij because I'll do it in 2D. And you define these occupation numbers n. So I have n for the liquid and n for the nanoparticles. I should say they don't really have to be nanoparticles. If you want to think about different size particles, that's fine. It just makes my life easier. So I either have liquid or nanoparticle or nothing in the cell, right? And that's the whole model. And then you define the energy of the system, and this has a few terms. These three terms here measure the, well, in our case, the attractive force between the different types of particles. So this first one measures the attraction between liquid and liquid particles, hence the superscripts at different sites. This is between the liquid and the nanoparticles, and this is nanoparticle. And these epsilons will be different strengths depending on what your types of particles are, so whether they're liquid or nanoparticle. Then you have an external potential, which I've labeled as phi. So this you can think of as gravity or attraction by the wall. So this acts differently, possibly on the nanoparticles and the liquid. So you have these phi's. And then you have something called a chemical potential that acts on the liquid that tells you how much liquid wants to be in the system. So you can think of this as equivalent to the humidity of the air outside your box that you're doing the simulation in. And if you change mu, it changes how much liquid is in your box. The droplet will get wetter or drier. Right, so you add all of these up and you get the energy of the system. Is everybody happy with that? I've not told you what any of the bits are, but that's the model. So I'll show you the dynamics in a bit. We're going to do the equilibrium first, and then I'll show you the dynamics. It's basically a generalized diffusion equation. Yeah.
And you ignore the initial spreading of the drops.
So I can
The
put,
starting point is when the drop has probably spread, considering one drop spread of its initial position.
so I can put on a droplet that has the incorrect contact angle, and I can then run the dynamics and it will run to the correct one. I've not shown you the dynamics yet. What I do in this is I will end up minimizing the free energy, but basically the energy. And then you can put in any initial configuration and you run your minimization routine, which in our case is a simple Picard solver, and it will iterate to the correct contact angle. But yeah, I will show you the dynamics in a bit. So I need to tell you about the pairwise interactions and the external potential. Right, so the pairwise interactions. So I had these. I should be able to get back. I have the keyboard as well. So
Yeah.
Realize I need to go back because I have got a click. I could have done it for that. Right. Okay. So I have these pairwise interactions and the external potential. These pairwise interactions. We basically do a simple model where you take your center point here, and then you look at the nearest neighbors, which are the green ones in a cube, the next nearest neighbors, which are the blue ones, and the next nearest neighbors, which are the pinky red ones. And these have different weights on them. So you fix an epsilon that's independent of where you are, so how far away your point is. And then depending on the distance you are, which is essentially this Cij, you put a different weight on it. So these are carefully chosen parameters that are related to discretizing the Laplacian. Basically, they're the correct parameters to give you a spherical droplet. So because you've discretized, if you don't pick particularly these values, so if for example, you turned off this 1/20 and put it to 0, you get weird rectangular droplets. Right. So in some way, this is the correct way of discretizing distance in a lattice. There's generalizations if you want to do it in 2D and with other things, but this is sort of the correct parameters. So these are related to the Laplacian, but they're basically this decaying attraction. So the further away you go, the lower the number is, and there's just this hard cutoff at more than next nearest neighbor. Right. So if you're outside this cube, the potential is 0. This is in some way justified by thinking about something like a Leonard-Jones attraction that decays relatively quickly. Depending on what your parameters you pick, the error is going to be a few percent. It really matters if you're looking at long-range attractions, so bringing things in from a long way apart. But if things are already close together, the error is relatively small doing this. And you can extend it if you want to do a bigger grid. It's just computationally more expensive and not particularly interesting. And then you have this hard sphere or hard particle exclusion by not being able to have more than one thing in your cell. So I have a hard core and I have a sort of an attractive tail, which is then cut off. So it's not perfect, but it's on a lattice and it's relatively cheap to implement. Okay. For the wall, I'll get rid of this so you can see the title. So for the wall, I essentially take an infinite wall of nanoparticles. Right. So then what you do is you take this infinite wall, which is infinite in space and in depth, and then you integrate this, let me go back, this interaction over the wall, and it turns out that you end up with a value which is -12/5. Right, that just happens to be the value that you get if you do this integration. And then have a strength of the wall, which is epsilon, and the strength can be different for the liquid and the nanoparticles. So they can be more or less attractive to the liquid and the nanoparticles. And then what I do is that acts on the lowest row of cells in my lattice. So if I'm directly on the wall, I feel this, otherwise I don't feel it anywhere. So it's the same sort of length cut up as I'm doing in my particle-particle interactions. If you want to be cleverer, you can make it decay slower, that's fine, and it's actually pretty cheap. But this is enough to do what we want to do. So that was how we set up these interactions. Now the question obviously is, how do you pick these parameters? And I'll talk about that in a bit. In particular, what's important. But let's look at what happens to get a more statistical model. So this would give you one experiment, right? Pick an initial condition, and it would tell you the energy of that. What I'm really interested in, what happens if I take a lot of experiments, what's going to happen on average? So if I think about taking all of these droplets that I create by putting my experiment on, looking where the liquid and the nanoparticles are, then I think about taking each droplet, let's assume they're the same size, I discretize them all in this grid, and I count how often I have a nanoparticle and how often I have a liquid, and that gives me a probability over all of these experiments of having liquid somewhere, having nanoparticles somewhere, having nothing somewhere. Okay, so I then have a grid sort of on the bottom here. I've not drawn the grid on, but you can probably see that there's a grid on there just by looking at the discretization. And then this is a probability on the right-hand side. And this is the probability of having, let's say, liquid somewhere in a droplet. So it's a high probability here, and then it smooths out the edge of your droplet, because in some of the experiments you would have had a water there outside the droplet, sometimes you wouldn't. So the probability here goes from 0 to 1. And then this is the same thing for the nanoparticles. And the fact it only goes up to like 0.2 is just that I've got fewer nanoparticles than liquid in the droplets. So you get this statistical average of a density. So this is the probability over lots of runs of having particle or water there. Yeah.
I'm sorry, can you put the questions now?
No, it's fine. Yeah.
Maybe you said it earlier instead. What kind of dynamics do you do? Is this a Monte Carlo?
So at the moment, we don't really. So I'm going to do some dynamics on these fields, so on these densities, and I'm just going to minimize the free energy. And I haven't said it yet, but I'll show you in a second. Yeah. So that was what I've shown you is, given a particular setup, I can tell you what the energy is. Given a lot of setups, I can compute some average. That's all I've really told you so far. So you can write down the free energy rather than the energy, which is basically the energy plus entropy. So this stuff on the third and fourth lines is exactly what I had before, except I've replaced these numbers by the densities. So this is like a probabilistic approximation to it, whereas, you know, I had ones and zeros before, and now I have the probabilities. And then these first two lines are just the entropy terms. So this is corresponding to like an ideal gas. Okay, so this tells you something about the statistics of the model. And then this is the free energy. And then what you want to do is I fix my epsilons, I fix my phi, I fix my mu, and then I minimize this over all possible densities. Okay, and that will give me my droplets in principle. Everyone happy? Right. So these are Andy's results, not mine. I did it and got the same curve, obviously, but the picture was in this paper already. So this is the contact angle that you get, which is sort of explained at the bottom. So big contact angle is almost spherical droplets sat on your surface. Small contact angle is something that's very flat. So you're sort of measuring the inside angle in some sense. is controlled purely by the ratio of the strength of your wall. So I only have liquid at the moment. So the strength of your wall compared to the attraction between the liquid. Right? The stronger the wall is, the more it sucks it down onto the surface. The less it is, the more likely your droplet just wants to sit as a circle or a ball, because it doesn't really feel the wall. So this is increasing wall strength, shows that you get decreasing contact angle, so your droplet spreads out on your wall until you get wetting, so it's completely flat film. The thing that's labeled DFT is what we've done. So it's called density functional theory. You minimize this free energy over all configurations, and it gives you this red line. And then this comparison with some Monte Carlo simulations, just to show you get qualitatively sensible things. But this shows you that you can take pure liquid and you can get a range of contact angles as equilibrium. And it just depends on one parameter in your model. Right, so in terms of dynamics, so that the equilibrium thing is called density functional theory because it's a theory of densities, and there's a functional of the densities that gives you the energy. For the dynamics, you do something called dynamic density functional theory because it's density functional theory that does dynamics. This is not, if you know the quantum chemistry literature, they also have density functional theory. It's heuristically or big picture the same idea, but completely different when you go to implement it. So if you, whatever you know from that, you have all sorts of different problems in the classical one. In some way, the quantum one is easier because you only have one type of interactions, which are Coulomb interactions. In a larger sense, it's harder because you have to have your density coming from a wave function, and there's lots more constraints. So they both have their challenges. But we're going to do it's often people call it classical dynamic density functional theory. So it's a generalization of the diffusion equation. Let me just go back and remind you that this F is this free energy. Right? So there's the entropy part and then the energy part. So what you do is you take the functional derivative of the free energy with respect to your two different components, so the liquid and the nanoparticles. You take the gradient of that, you multiply it by the density that you had, you multiply it by some mobility matrix or function. That tells you how easy or difficult it is for things to move around. I'll talk about why we've got that in there in a minute. And then you take the divergence. So let's reduce it to something much simpler for people who haven't seen this before. The mobility coefficients are all now 1, so m is 1. df by d rho is going to be, f is going to be log of rho. So then it turns out that the gradient of df by d rho ends up being, so rho log rho, and then the gradient of df by d rho ends up as being log rho divided by rho. No, sorry, grad rho. Let me start again. This whole thing here, grad df by d rho, gives you gradient of rho divided by rho. Let's skip all the intermediate things. So this gives you rho times the gradient of rho divided by rho, which is just the gradient of rho. So this just gives you the diffusion equation, right? And that's exactly what you would get if you set all of these epsilons to be 0. Right. So that's exactly what we're going to do, except we're going to take this more complicated functional that includes the external potential and the interacting particles. So this is the system that I solve when I solve the dynamics. I take some initial condition and some appropriate boundary conditions because it's a PDE. I'll tell you about them in a minute. And then I have to give you also these mobility coefficients. Just to note that these operators that I've written as the standard divergence and gradient are actually finite differences because I'm on a lattice, but it makes no difference. You can solve the continuum version of it. In fact, that's what I was trying to do that didn't work when they originally showed me the thing, and then I decided to do Andy's lattice model because I knew it would work. Right, I need to tell you what these M's are, and I need to tell you how I do evaporation, because I've not told you that yet. So what you do with these M's is, apart from at the layer that's at the wall, they've just 1 everywhere. So you just diffuse normally, so you just get the standard homogeneous isotropic diffusion equation. The thing that you modify is the rho that's near the wall. So this is supposed to implement sort of sticky no-slip walls so that I can fix my contact line, for example. So what I do with that, and when I say this is what Andy did with this, and then I copied it. So you've got 2 directions that are parallel to the wall, which are the X and the Z directions. Okay, so the first and the third components, and you've got something that's perpendicular to the wall, which is the Y or the middle component. So parallel to the wall, I do the same thing. Again, I'm going to be in 2D, so there's really only one of these, but let me explain it in 3D. You put something that's called S, and that determines how easy it is to move if you're sat next to the wall, parallel to the wall. You can set this to whatever you like. If you set it to 0, it means nothing can move along the wall. Right? So you're like, oh, I'll implement no slip boundary conditions. And what I'll do is I'll just make it so things can't move across the wall. And then you run your code and the droplet spreads. And you're like, well, why is that happening? Turns out what happens is you think about having a particle on the wall. All it does is it moves up one with spacing, moves across, and then moves back down. So you just get sort of hopping particles that look exactly like a droplet spreading. So that doesn't really achieve what you wanted to do. So what you can then do is modify the vertical diffusion away from the wall. So it's a small number, and this stops you too often going up and across. So you can still spread by going up and across, but the probability of that happening or the time scale it happens is much longer. So it doesn't happen as much, so you can control how much you spread out. And fiddling with these S's and these U's can change the dynamics depending on what you would like your contact line to be doing. Right? There's no microscopic physics in this. What you should really do is make your wall rough and have pinning. But this is sort of a macroscopic way of enforcing that. And then just in terms of what you do for the mobilities, other than that, if you're the liquid, you just move freely. So that just diffuses like normal. And then the idea is that the particles only diffuse if they're surrounded by liquid. So if they're sat on the surface, they should stay there. Otherwise, what happens is that you run your dynamics, your water evaporates, and your particles carry on moving, which is not what happens in the experiment. So you change your nanoparticle mobility to depend on the liquid density. The key here is that the mobility is 0 when there's no liquid, and it's, well, in some sense, 1 or some other constant when it's completely surrounded by liquid. Okay, and then some smooth interpolation between it. This is some smooth interpolation between it. It genuinely doesn't really matter what you do here. The dynamics are qualitatively similar as long as this curve looks similar. Okay, so this basically stops the nanoparticles from moving whilst they're dry. So again, that's probably something you should get from a more microscopic approach, but this is on the level of a cell. How do you enforce these things? People happy with that? So that's mobility coefficients. I still need to tell you how I do evaporation. So how they do the experiment is they put the droplet in a box, which has sides and an open top, right? So what we do is we have a box, and at the top, at each time step in my dynamics, you set the top value of the top row of your domain to be some constant, which is basically the density of liquid in the air. So it's the vapor, right? And you update that at every time step. And so what will happen is if your box is drier than your air, it will force liquid into your box. If your box is wetter than the air, it will get sucked out. Okay, so this is like changing the chemical potential if you're thinking about going to equilibrium. Now, the speed of evaporation depends on the size of your box. So the further away you put the top, the longer it takes your liquid to diffuse in or out, right? If your box is sufficiently big, all it does is change the time scale that your dynamics happen on. So you can just rescale time and they look essentially exactly the same. If your box is too small, you get a very different result. The easy way of seeing that is, imagine I make my box so small that it intersects the droplet. Then immediately I set the top of the droplet to have very little liquid in and I get garbage. Right? But even if you're relatively close, it does change the dynamics. So you just need to fiddle with your numerical scheme and make your box bigger and bigger and bigger until it seems to stay roughly constant in the box size. Yeah, so that's what this, otherwise basically what you're thinking about is your droplet, there's sort of two timescales. There's your evaporative timescale and the timescale your droplet does stuff on. So your droplet sort of instantaneously equilibrates and then you remove some gas and then it does it again. So if you're far enough away, those two timescales are very different. So I'm happy that the numerics we've got in the results are independent of the box size. And then in the other sides of my 2D box, you can basically do whatever you like with the droplets in the middle of the box and not a lot happens. If you want to evaporate them, you can, and it changes the evaporation time. If you want to put a hard wall there so nothing can move through it, you can do that. All we do is we make it periodic in that dimension, but the droplet is going to be like the middle quarter of the box or something, and my interactions are only one lattice site, well, 3 lattice sites wide, so you really don't see the effects of the boundary. And the advantage of making it periodic is you can make sure you conserve the number of nanoparticles in the box without doing any horrible numerics. Right. So let me show you some results for an evaporating droplet of water with an initial contact angle of 120 degrees. So the only things I've fitted in my numerics are I've fiddled with the wall parameter the wall strength, so I get an equilibrium contact angle of 120 degrees. That's changing that one parameter. If you change it, you get a different experiment, so you can compare to that as well. I've set the time scale by how long it takes the droplet to evaporate. So the standard is that you wait until 90% of the volume of the droplet has evaporated, and then you determine that as your fixed time point, and you match the two things. This is what people do when they match experiments as well. It's 90% because below about that, it gets hard to measure your droplets. And we'll see some results that show that in a minute. And I've also fixed my length scale, because my length scale in my simulation is essentially arbitrary. And that's where this dropper comes in, so you know how wide this is, so I know how wide a pixel is, and I just make sure that my initial contact line here, width of that is the same width as this when I move it over to the other picture. Right. There's a magenta line here, which is the outline of my droplet, and there's a green line that's hidden underneath it because it's pretty much the same to start with, which is the one from the experiment from the first movie I showed you right at the start. And we're going to watch them evaporate. So what you should hopefully see is that the magenta line basically lies on top of the green line. It'll jump about a tiny bit because there's a lattice. But broadly speaking, you get quite good agreement until your droplet becomes quite small. And I know why it goes wrong then, and maybe we can talk about that at the end. So we were pretty happy with this. So I didn't have the experimental results until I'd done the numerics. And then I gave them, then I said, can I have the experimental results? And I compared it, I'm like, oh, that's much better than I thought it was going to be. So that was very pleasing. That was a good day in research. So we're happy with this. So what we then did was Carmen was doing experiments with different contact angles. So you do this by doping the surface. I'm not an experimentalist. Please don't ask me very many questions about the experiments. They dope the surface with different things, and you get different equilibrium contact angles. Whether it changes anything else at the same time or not is another question. Let's assume that it doesn't. So you've got a range of different contact angles going from about 38 up to about 105. Yeah. So again, I said, well, give me the contact angles and I'll run the experiment, the numerics, and I'll plot some things that you're interested in. And what they're interested in are things like the contact angle, the width of the base, the height of the droplet, and the volume that it contains. And they were measuring these over time. So what I did was I gave them my data and then Carmen plotted it. So just to go through, this is time in seconds. Again, my numerics are scaled to match their time scale. So it takes roughly 20 minutes or so for the droplet to evaporate. This is the contact angle in degrees. This is the volume. This is the base width. And this is the height. The three green lines are the three experiments that Carmen did for this particular contact angle. And the black line is the results of the DDFT. So we were pretty happy with that. I mean, if someone gave me that and said, does it agree? And if somebody else was also, I would say yes. So this is what I mean here about it being difficult to measure stuff once your droplet becomes too small. So actually, this is probably noise, like just from trying to measure stuff that is very small. So don't necessarily take into the fact that this dips down and this dips down is probably a happy coincidence rather than necessarily being both of them are correct. I'm confident that my results do that because I can measure my contact angle very accurately, but whether that's what's actually happening in the experiment is another question. But broadly speaking, the agreement's pretty good. So then we did it with these other contact angles. So this is for 55 degrees. You can see it's a little bit worse. Some of the things are still basically within the error bounds by taking the experiments as your error bounds. The thing I should say is that to determine the contact angle in the numerics, you have to set a density at which you fit your circle. So I fit my circle to a particular density, and then I compute a contact angle by working out the angle between that circle and the surface, which is just trigonometry. Now, this is relatively strongly dependent in some regimes on what you pick that value to be. Right? Traditionally, you would pick half the value between your liquid density and your gas density, which is basically a half. Right? But if you fiddle it a bit, you can make these curves agree a lot better. However, I've just picked what you pick as the standard and gone, well, that looks okay. So you can make these results agree better with the experiment, depending on how you define where your contact line or the edge of your droplet is, which is very easy to see in an experiment because it's one particular experiment. But when you do this sort of statistical averaging, it all smooths out the interface, and then you have to pick where you want to pick on the interface. So I can make these better if I want, but I'm happy with these. So basically, you see what you would expect, right? In these cases, what happens is the droplet sits there with essentially a constant base width The contact angle shrinks down, which means the droplet's getting flatter because you have to reduce the volume somehow. The volume decreases almost linearly in time, and the height also decreases almost linearly in time, which suggests you can probably get these results out with a much simpler model. And you can, but then you can't do these slip dynamics and maybe change the surface to be heterogeneous, and you can't also include the particles, which is what we're really interested in doing. So we then did it for a couple more contact angles. Again, they look pretty good. You can tweak them so they're better. But I mean, I'm just showing you the sort of honest results of what you get to start with. And then finally, you plot these results and you're like, oh, well, that's disappointing because that doesn't look as good. Now, bear in mind, the 120-degree one looked absolutely fine. So that was the one where I plotted the curves against each other. So it's not that big contact angle is bad, because that was fine. I mean, I could plot the same curves on here, but you could see from the two, the green and the magenta circles, that they were pretty good. So what this is because you're getting these two different types of dynamics that I described at the start. So here you're getting this constant contact line and changing contact angle. And then at some point in time during the experiment, it changes to being constant contact angle and changing base. So these are sort of these two naive regimes I explained at the start. Now, this isn't because something's changed in time, it's because it's hit a particular part of the surface and now it's doing something different. So the first thing the experimentalists said was, could you just change your model at that time point and show you it gives the same results? Like, I can, but it's not very honest, is it? And well, how do I know what that time point is without doing the experiment? So I sort of said, that's not what you should do. We should do surface roughness and make sure that we can work out how this happens. So that's on the to-do list. So you see that the volume plot is still reasonable, right? So the volume still decreases in roughly the same way. So that's okay. But then because you're in these different regimes, you get completely the wrong contact angle in my simulation, right? And you get completely the wrong height in some sense, because whether you're fixing the base or whether you're letting it move changes the height of the droplet of a fixed volume. I should probably say that these three things are all interlinked. In fact, they're all interlinked, but these three things are very much interlinked, right? If I give you two of these things and I tell you it's a circle, you can tell me what the other one is. So the fact that you get all three right is not surprising. The fact that it's a circle at all and you get two. Right, so then the question was, can you explain this with the model? Not necessarily the fact it changes at a particular time, but could I say I started here with this droplet, could I show you some dynamics that do constant contact angle but changing base? So my droplet does this. And this is all to do with this slip at the wall that I described. So I'd set these two parameters. Let me go here. So I set these two parameters, S, which tells you how easy it is to move along the wall. So I'd set this to be 0. And nu, which tells you how easy it is to hop up and down. Right? Turns out if you set S to be 1, doesn't really matter what you do with nu, everything looks about the same. So what we were looking at was the case where S is 0, and then what happens when you change this nu. So what I'm changing is how easy it is for my droplet to go away from my particle, to go away from the wall, and then move across, and then come back down. So this is going to model in some way, not necessarily with the correct physics, but in some way how easy it is for my droplet to spread. Okay? So if I make this nu bigger, my droplet should be able to, well, in this case, because it's evaporating, it contracts rather than spreading, but spread just means move sideways. So how easy it is for the base of my droplet to change length. So what I'm going to show you is what happens when you do the same simulation, but you use different values of nu, right? So the pink lines of the experiment again. This dark black line, well, they're basically the same. These two lowest ones, I actually did 10 to the -5, but the black one is 10 to the -6. So these are basically what I showed you before, where it's a very sticky wall. So you can't move up very easily. And then you increase nu, and you move up towards the curve. And I could fiddle this and I could find a value of nu that does the right thing and it would stick here, right? So it would show you it would show you a flat slope. I'm just not doing it. These are going by orders of magnitude, right? I can fiddle this, so this is 0.05 and it might look correct. But I want to show you that you can get this continual range in the model between completely slipping dynamics and basically completely sticking dynamics. This weird oscillation up here is because I've got a grid. And it just depends on, it will basically stick to a grid point and then it will suddenly move to another grid point. So that's why that happens. If you make the grid finer, these sort of go away. You still see them towards the end when your droplet is very small, but they go away in the bulk. So this, I understand why it happens. This is not really supposed to be the main high quality numerical results. It's just to show you that you can get these dynamics. So you can go smoothly between these two regimes. Obviously, real world droplets also do something in the middle as well. Not all of them just do stick or slip. You can get stuff that does sort of stick slip behavior or does both at the same time. And this will model that. Right, so that's all been on pure water droplets because the first thing I want to do is check that that worked. And I was quite happy with that. I mean, as a mathematician, that was a pretty good result for me is DDFT agreeing with experiments. I should point out, I think there's only one other paper that compares dynamic density functional theory to experiments. So it's a fairly novelty in that community as well. I mean, there's thousands of papers on it, but very few people actually compare it to experiments. I think probably because it's hard to find friendly experimentalists who will let you ask them stupid questions for weeks. So this was the prediction at the start, right? So this is what I showed you on the first slide. So coffee ring happens when the dynamics go down and out. Uniform deposition happens when you go round and round. And then the equivalent is that no slip tends to give you a coffee ring because it forces the stuff to the edge of the droplet evaporates. If it's slipping and the droplet is reducing in size, it puts deposits as you go along. Like this is another heuristic for why it happens. These are some snapshots of what the flow is doing inside my droplet for my no slip condition, which is like my nu is very small, and my slip condition, which is nu is very big. So you see that this one on the left pretty much agrees with this picture, right? It goes down and out. The one on here goes in and up. You don't see the circulatory pattern, but that might be a dynamical thing. So you sort of get the same patterns, but the question is that really what's causing it? And these are just snapshots, right? You don't know that I've not just picked two particular time points where they look correct, right? So these are the movies. This is the liquid on the left. No, so these are both liquid. So this is the one that corresponds to A. So this is the first picture where I basically have the flow that should go like this. And this is the flow that I would like to see being circulatory if the heuristics are correct. And that's also the reason in my model. I don't care if it doesn't, because my model is going to be fine, but let's just see what happens. So there's a bit at the start where it's a bit messy. And what you're going to have to do is average in your head over time to see what happens most of the time. So most of the time, the one on the left goes down and out, right? And then most of the time, the one on the right goes up and maybe round a little bit. So they are doing qualitatively what I showed the snapshots to be doing. You can also see that the contact angle here is changing, and the contact angle here is roughly 120 degrees for the whole time. So this is fixed contact angle, and this is fixed contact line. I could plot the base and it stays about the same as well. So that's what's happening in these dynamics. So my prediction, if you actually measure these flows, is that's what happens in our dynamics. Whether that's what happens in the true droplet is another question. So that was, I should say why I'm doing this. So in case anybody doesn't do modeling, all models should be predictive. Right? If your model doesn't make a prediction, it's just stamp collecting and you're just fitting curves through things. So I would like to make a prediction that I haven't seen in the experiments, preferably a prediction I could test. So this is one thing we're looking at. And then my other prediction, we're going to go back to the coffee ring. So what I would like to see is that the model can produce something that looks like a coffee ring with a particular set of parameters, right? I don't know what some of my parameters are. So I don't know what these interactions are between my water and my colloid. You can estimate them with various potentials, but I don't know what they are. And the model does depend on what they are. I don't know how big my droplet is, and it depends on that. So what I'm going to show you is one particular set of parameters that I picked, not particularly carefully, I should say. This is the liquid on the left. So you start with some particular contact angle, which is about 105 degrees. That's because that's one of the ones they did in experiments. And this is the density of the nanoparticles. Notice that the density here is much lower. So this scale here is like 0.04. So this is a few percent particles. What I'm going to do is run the dynamics. And these are great when you plot them while it's doing the computation, because you sit there and you go, actually, let me pause. You sit there and go, well, what's going to happen? And these take like an hour or so to do. So you notice you've got a ring, so a brighter area of particles at the edge of the droplet. So when I showed this to the experimentalists, I went, I've got this weird effect. I see more particles at the edge of the droplet. And they went, oh, so do we. We thought we were measuring it wrong, but it was a weird effect. So we're also happy about that. So yeah, you run these and you sort of output your results and you go back and you look at them occasionally. And you're like, is this going to make a coffee ring or is this going to sit there and do nothing? I think that there's a clue in the title of the slide, but at this point, it doesn't look like it's going to do very much, right? I've got this sort of profile here. But eventually what will happen is you will get two lumps, one here and one here. So it all happens towards the end of the time. So now you get two lumps. So there's a few weird things going on. They're floating on the surface. That's because there's still a liquid layer stuck to the surface. And this is a consequence of the no flux, but we're not too bothered about that. You probably can't see very well, but there's actually still some particles left in the gas, but that's just because it's statistical and because the dynamics don't drag them off the surface. But if you imagine this is a 2D slice through a droplet, rotate it around in your head, so you get a ring. So you can produce copy ring-like effects without putting in explicitly hydrodynamics into your model. Right, so this is a statistical mechanics model that gives you coffee rings. So then the question is, are the standard explanations correct, or do you need to go back and rethink what's happening? Might be, well, it certainly is that multiple models can give you the same sort of outcomes, but do you need all the complexity if you're doing this? So this I was very happy with, and we have a lot more examples with fancy coffee rings and all sorts of things happening. Currently what we're doing is waiting for a new PhD student to do the rest of the experiments. But Carmen has some results, so we're comparing those. And then we're also working with a postdoc in Denmark. So what we want to look at is whether these are reasonable compared to what you get in experiments. There's a lot more parameters to play with. So before I only had one parameter, which was the strength of the wall. Now I have these sort of three interaction parameters that I need to worry about. So trying to get exact matching with experiments is going to be harder, but maybe we can get qualitative stuff. We also want to look at making the wall genuinely rough, so spatially rough, and see what happens. And I will stick up my conclusions. The one thing I want to highlight is despite the fact I probably thoroughly confused you, it's a relatively simple mathematical model. So it's a lattice model. You don't do anything particularly complicated, and you get very nice results that match very well with experiments. As I said, this is basically the first time people have tested these things against experiments. And there's a lot of work to do to actually get agreement with, or find out you don't get agreement with experiment that I would also be happy with. That's also fine for me. If I show that the model doesn't work, I'm also happy with that. So I'll say thank you very much for listening to me and stop talking.